Hi, I'm Walter Shceirer from the University of Notre Dame, and today I'm going to be giving a talk in this workshop on visual psychophysics as an evaluation regime for object recognition. For a number of years, I have been thinking hard about this question of evaluation in computer vision. Are we doing it correctly? Are data sets the only way we can perform evaluation? These are some big questions that I feel need some more consideration so we can make progress on problems like object recognition, object detection, related recognition problems, things of concern to this particular workshop. So I hope you enjoy this talk. So to begin, let's imagine the following scenario. And perhaps this isn't too hard to imagine for many of you. I know the organizers of this workshop are roboticists. And roboticists, of course, have been thinking a lot these days about autonomous systems, right? Like self-driving cars and the safety of these systems. Very, very important questions related to safety have surfaced recently, and the entire industry is thinking hard about this. So imagine, for the sake of this example, that a proprietary autonomous vehicle system purportedly solves driving with human-like ability, right? This new system has appeared. The designers and implementers of this system are making this big claim that this system is human-like, right? We've solved it. Let's ship it. Let's get it into the hands of consumers and move on with marketing this great, wonderful product. By all accounts, the software achieves superior performance on established computer vision benchmarks. So this would be standard dataset testing, which is standard operating procedure throughout the autonomous vehicles industry right now. And of course, right, we've made great strides in computer vision at large using these benchmark datasets like ImageNet, COCO, et cetera. So this would be fairly compelling, right, if the designers had published this paper. But perhaps we're a little bit more skeptical. And we want to ask the following question. How would we go about falsifying the claim of human-like ability in this particular instance? And this is a very, very important and interesting question because computer vision, robotics, these aren't the only fields thinking about vision, right? In fact, there's a much larger scientific community in vision sciences at large that for many years, right before there even was a field of computer vision, we're asking big questions about some of these same issues. And so that's what I want to get at in today's talk here. So that takes us to a classic thought experiment from philosophy, the Chinese room. And this is a great thought experiment as it relates to artificial intelligence. And I think it's quite diagnostic for the situation that we find ourselves in the present day, thinking about evaluation and computer vision. So if you're not familiar with this thought experiment, let me walk you through it. Number one, this was proposed by John Searle in the early 1980s, specifically related to dilemmas in artificial intelligence. Big questions surrounding what is an intelligent system? How would you figure out if a system truly is intelligent? Right? There's some basic questions we need to ask when we're dealing with anything in AI that is meant to mimic some competency of the brain. All right, so here's the thought experiment. Imagine there is a box and there is a man in this box, as we can see here in this diagram. And the man in this box does not speak the Chinese language. But this man can communicate in some sense with people outside of the box who only speak Chinese because he has access to a codex, which maps symbols to other symbols. And so when he gets some sort of input into this box, right, which has a Chinese character, he can consult his codex and find the appropriate response in his box, which he has access to with all these other symbols, and he can send that outside of the box. And so what's interesting here is that the people outside of the box may believe that the man inside the box knows their language, right? Because he always has an appropriate response because he has access to this lookup table. But of course, it's a ruse, right? The man has no knowledge of this language. So, you know, it's sort of duping those outside of the black box into thinking, right, that there's more going on behind the scenes when unfortunately it's just a lookup table. So what is the relationship between this thought experiment and what we see today with respect to, say, deep learning, right? We We have artificial neural networks that are, in many cases, massively parameterized, right? Millions, many millions of parameters. And what we have in that kind of scenario, in many cases, is something akin to a lookup table, right? There's been some recent discussion around this idea that a neural network at that scale is nothing more than a lookup table. Think of recently introduced models like GPT-3 from OpenAI. This is a very large language model which has an enormous corpus baked into it. And that isn't great if you think about what representation learning is trying to achieve, because there really is no compressed representation. It kind of spits back out the language that it's ingested. And we see this with a lot of different computer vision models as well, especially generative models, right? Think of GANs. In many cases, right, the objects or faces that are synthesized from these generative models look suspiciously similar to the training examples, right, that were used to create the system. And again, if you think about it, it's not terribly surprising, right? If you have a large memory, what you're going to do is end up recalling things from that large memory. And so that's not great, right? Because we wouldn't need to learn from data to perform that exercise. We could just use a database. We could use some other data structure, right? And a lookup table. These things are well known in the systems world. There's absolutely no reason why we would have to go to learning from data for many of these cases, if that's the functionality we wanted. Of course, we want something more in AI systems beyond just that lookup table. All right, so how do we deal with this, right? How do we know if we're dealing with a Chinese room type of scenario? Enter visual psychophysics. This is a set of methods and procedures from psychology which are used to probe psychological and perceptual thresholds in humans who are participating in a study. This could also be used in a neuroscience context to probe animals. And what you're going to do here is have very controlled manipulation of the stimuli which you show a subject or an animal, and you're going to measure the behavioral response. So this is different from other forms of experimentation in brain science, like something non-invasive like fMRI, MEG, EEG, or perhaps if you're dealing with animals, it could be something more invasive like electrophysiology. Here we just want to measure the behavior. And this becomes a great way to do experiments in computer vision because we can easily get human subjects for human baselines, and we can adapt these methods and procedures to computer vision evaluations. And I'm going to talk about that in this talk. So the careful management of stimulus construction, ordering, and presentation allows for the precise determination of these perceptual thresholds. And the stimuli you construct can be rather unique, right? You can imagine trying to study something about facial perception, and you can alter the coherency of face parts, right? We can adjust the attributes and figure out at what point is a face so scrambled that somebody can no longer tell that it's a face, right? What's the limit of what facial processing can do? That would be a question you could ask. Here's another example of that. This light bulb looking man, it's a cartoon, but I can still tell, right, that that figure in the upper left is a face. My mind still interprets the one next to it as a face, but it's kind of a weird scrambled face where the parts aren't in the right place, and it looks like the eyebrows are taking the place of the eyes, and the nose is sort of misplaced. And there's another set of eyes below, but I can still kind of get a face-like interpretation from that. And then the others, right, I just don't perceive a face at all. That looks like abstract art. But this gives you a sense of what's going on here with visual psychophysics. There's going to be at some point at which the system breaks, right? We can no longer recognize what is being presented in front of us, right? And that's important to know because that gives us some bounds on the limits, right, that these systems have. And again, this could be a biological organism, or, right, for our purposes, it could be a computer model, right, of some visual competency. This is not a new idea. This is not something fresh that I have pulled from the psychology literature. Visual psychophysics has been around for many decades. The canonical early example of this type of experimentation is the minimum threshold for the stimulation of an individual photoreceptor. This is a classic experiment from the 1940s, and that minimum threshold turned out to be a single photon. And I like this example because it highlights how powerful visual psychophysics can be. if I can manipulate the stimulus down to a single photon of light and build up from that, basically can construct any type of visual stimulus I want, right? From very primitive light levels up through very complex natural scenes. All right, so let's take this back now to computer vision to try to figure out how we can use this in a setting which will help us evaluate things like object classification systems, object detection systems, right? These commonly used recognition systems within the field. So here's the traditional setup. Here's a little example. I've got some data set, maybe it's ImageNet, as we can see here. And I have two different algorithms. I have algorithm A and algorithm B. And each of these algorithms is meant to operate in an image classification setting. And I'm computing some evaluation metrics here, namely top 1 and top 5 accuracy. And I'm going to test both of these algorithms over the same exact data set. And I'm going to record the top 1 and top 5 classification accuracies. And whichever algorithm scores the best on these metrics, I'll say is the best algorithm. That's the one I want to use in operation. Right? This is typically what we do when we do evaluation for publication purposes, right? Countless papers published in this regime. What we do in an R&D setting, if we're at a company, to figure out what we should put into our autonomous vehicle, right? Nothing surprising about this. And if we look at the results from our little experiment here, looks like on both of these statistics, I'm going to use algorithm B. It's clearly better, right? 89.2% versus 91.1% on top 1. 98.6% versus 96.3 for top 5. In both of these statistics, B is superior. Why would I even consider A? All right, so here's why you may want to rethink that. Let's turn to a psychophysical evaluation. So first, we have to think about our stimuli. We could have natural stimuli. We could just take the data set we used in the traditional setting. I could just take ImageNet and move it over here. Or I can have rendered stimuli, which would be a little bit more controlled. If I'm using procedurally rendered graphics, I know all of the parameters that went into the scene, so I don't have to stress too much about noise contaminating things. Because ideally, we want to start at a place which is perfect, where the system is not failing. And then, right, as we control some variable, we can figure out where the system fails with respect to that particular variable. So that means we're going to have to change these base images in some way. And so we can pick a series of transformation functions. It could be something like Gaussian blur if we're trying to study motion or resolution. That could be something like linear occlusion, right? I know objects are going to appear behind other objects. That's natural. We see that all of the time. Something we would want to understand. And then rotation, right? Another basic transformation. And something that ideally, right, if we're using a machine learning-based system, we would be invariant to. And now what we're going to do is turn the crank ever so slightly. So as I mentioned, right, we want to ideally start at a place where the performance is perfect or near perfect. So if we look at the plots here on the right of panel B, we can see what are known as item response curves. And so we would start at the upper right, where we can see if accuracy on the y-axis is from 1 to 0, where 1 is at the top, 0 is at the bottom. So it would be worse right at the lower left. We're starting at a really good place, right, in all of these cases. And we're going to, on the x-axis, then increase the level of transformation. So that first plot, we're increasing the blur, adjusting the sigma parameter, right, to increase the amount of blur in the scene. Same thing, increasing the percentage of occlusion, changing the rotation degrees. All of that follows on the x-axis. And as you see here, right, as we turn the crank and we add more and more of whatever condition we're trying to study, the performance of both of these algorithms is dropping. But what's interesting here, for the case of model A versus model B and Gaussian blur, model A is better than model B for this particular condition. That's something that was not reflected in the summary statistics we were examining for the traditional evaluation case. The same thing is true of linear occlusion, right? Model A is the model I want to use when I expect occlusion in the scene, not model B. But if we look at rotation, model B is pretty stable, where model A is highly impacted by that particular condition. All of these observations could not be discerned from summary statistics because the errors are just baked into the overall summary, right? We have no picture of what is causing the system to fail. Now, of course, we could pull all of the failure cases out of the data set and inspect them one by one. But if some of these things are latent parameters, it may be very, very difficult to understand what exactly caused the system to fail, right? In some cases, things like blur can be very, very subtle, right? To the human observer, it may not become apparent that that's affecting the artificial visual system. But if we've started at a place, right, where we know the system is working, and then we force the system to break by controlling a particular parameter, then we know exactly what caused the failure. That's the power of psychophysics in this context. So I'm going to talk about a few papers in the rest of this talk, which provide a little bit more detail in terms of how you might do this for things like object recognition, face recognition, and image enhancement and restoration for recognition purposes. So this first piece of work is visual psychophysics for object recognition. This is work that was led by my graduate student, Brandon Richard Webster, in collaboration with a small company, Perceptive Automata, which I co-founded in the Boston area. And Sam Anthony is the tech lead, CTO of Perceptive, and a card-carrying psychologist. So we really wanted to bring in some interdisciplinary expertise. And this work really comes out of psychology, more so, I'd say, than classical computer vision. So it was a really nice blending of all these different areas. This is an article that was published in TPAMI last year. All right, so here's the process again, but with a few more details. So as I mentioned, right, you got to start with your data, right? What are the stimuli? So we're going to choose, right, natural or rendered images. Now, here's an important missing step, right? I mentioned we want to start at a perfect place because then we know whatever we're doing to the scene to alter it is what's changing things. And we call this process finding a preferred view. If you dig into the psychology literature, you'll find work on human vision related to the study of what is known as the phenomenon of canonical view. This is really interesting because psychophysical experiments have shown that people prefer certain orientations and configurations of objects to be able to recognize them very quickly. And intuitively, this makes sense because if I see the front of a chair, I'm going to easily recognize it as being a chair. If I am given an alternate viewpoint of, say, below the chair, looking at the bottom of the seat, I may be very puzzled because that is not a viewpoint I typically experience, right? And it may take me a few moments to figure out, oh, this is probably a chair, right? So there's some difference, right, in the reaction time and maybe even the accuracy. In some cases, I may see a viewpoint of a particular object, which again, it's so far beyond my experience, I can't figure out what that object is. And so what we want to do then is try to figure out, like we can figure out using psychophysical measurements with people, what the preferred view is, what the canonical view is. We want to find what the preferred view is for a model. And we don't restrict that to just one particular view. There could be several preferred views that a model is able to respond to. And that probably maps back to the training data, right? What viewpoints were provided to this system as it was trained, if it's data-driven, and what does it respond to quite strongly. So this is a process where we're going to feed a bunch of images into whatever model we're trying to study is, and then we're going to measure the scores coming out of it. We're going to try to find, right, the places that are perfect or near perfect. And we're going to retain those as our set of stimuli, because that's going to give us a good point at which to start degrading. And then we're going to transform these images with whatever transformation functions we want. So this could be, as I mentioned, Gaussian blur, linear occlusion, or rotation, but it could be other things as well, right? And I'm going to show you a whole bunch of different examples. Some of them just basic functions from image processing. In other cases, more semantically meaningful animations or manipulations of a 3D model. All of this is possible. As long as, again, we have a procedure to control this, it's going to work out for the psychophysics experiments. And then the final step here is to generate item response curves. We want to have some way to summarize this experiment and ideally give something that's intuitive to the human to interpret so we can understand what's going on. So if you dig into the psychology literature, you'll find a whole bunch of different commonly used experimental protocols. And perhaps one of the most familiar is the two alternative first choice task, or 2AFC. And some of you may be familiar with this if you've ever participated in a study. Maybe, again, you were an undergraduate trying to get some extra credit in a course, and you drop by the psych lab, right, to do a study, trying to help out your friends who may have been graduate students in the lab, et cetera. It's a very, very basic idea. So you're going to start out with a sample stimulus, in this case, right, this airliner. You're going to be presented with this. It's going to disappear on the display, right, that's being used for experimentation. And then replacing it, it's going to be a matching alternate stimulus. So this is a different viewpoint of that plane. And then a non-matching alternate stimulus, this friendly dog. And this example looks pretty easy, right? But in practice, it's going to go by very fast because human vision is quite good, right? And rapid presentation time will bring humans off of ceiling. But we can perform the same experiment to a model where the reaction time isn't really as consequential, but the accuracy of this process would be. So this is almost like a pair matching task in computer vision. And what we're going to do is that basic process, right, over and over and over again. We're going to first start with a set of models, which we've taken from standard off-the-shelf common code repositories. So looking at the things we use all of the time as baselines in object recognition tasks, like AlexNet, CafeNet, GoogleNet, 2 versions of VGG. We're going to find the preferred views, as I mentioned, right? We're going to find some set of images, and then that these things are perfect or near perfect on. Then we're going to start turning the crank on a particular condition. So in this case, we're looking at Gaussian blur. So on the x-axis, right, we can see the different values of sigma, which is going to control the amount of blur in the scene. And then we can see some examples of a 3D rendered tiger. And we can see here, right, as we increase the amount of blur, this does become difficult. In fact, there is a point at which people will fail at this task, but in this particular case, it turns out that that's far beyond where the computer models are failing. In fact, this is an interesting case because blur severely impacts the performance of all 5 of these particular image classification networks. And we also plotted a human point here for reference. So accuracy, right, in an item response curve is on the y-axis, 1 to 0. And we can see here, right, that the humans are superior to all 5 of these networks as we go along. And what's really interesting is that the networks are failing at a place I'd say most people who have at least average vision would not be foiled at, right? It looks like we're starting to see a lot of failure between 9 and 6 sigma. It's going to get progressively worse and worse. And humans are still performing really well at points, right, where accuracy has dropped, in some cases, dismally low, right, 0.4. GoogleNet is highly impacted by blur, right? It's hovering above 0 here. So this is pretty drastic in terms of the impact of just this particular condition. Now, what's interesting here too is that all of these networks have been trained on the same exact training data set. They're all trained on the same partition of ImageNet. But we can see that different choices in the architecture of these networks and also, right, different choices of hyperparameters that went into training them has changed the way they behave, right? They're not all in sync, failing, right, in tandem. There is a lot of variance in terms of what we see in terms of the impact of these conditions. Same thing is true of rotation, but not quite as extreme. This is a case where all of the networks are pretty tolerant of the condition, but some networks are better than others. In fact, VGG suffers more than CafeNet and GoogleNet. AlexNet is just a little bit better than VGG. But compared to what we saw with the blur scenario, this is much, much better. Right. In fact, we can almost say that CafeNet and GoogleNet are on par with human performance. Again, there's a red point there for this rotation of 180 degrees, and not much of an impact there between the models and the humans in those particular cases. So this is great. We can get a picture of what transformations are highly impacting the system. We can have a more or less fair comparison between human performance and machine performance, and we can get all this information summarized visually so that it's interpretable. But you may be saying that 2AFC task is not that realistic, right? Usually when we have something like a classification network, we have a very large gallery of images, right, that these systems have been trained to recognize. So what we've done is expand the 2AFC task to something we call the MAFC task, where we have a probe image and we have a pre-trained classification model which has many classes. And the idea is, did we correctly identify the class, right, that corresponds to the probe image with a high confidence, right? Is that the top score? Now, when we really dig into these experiments, we find some really fascinating results. In this case, a curious contrast deficit is present between what we see in human vision and what we see in the machine vision. So what am I talking about here? Human vision has problems with contrast related usually to low light conditions. Night blindness is a common problem that we hear about when it comes to human vision. And this is a serious consideration for things like autonomous vehicle systems, where we would want the system to behave safely at night, perhaps more safe, right, than humans. And the good news here is that when we decrease contrast, this is not the impact that we see with humans. So again, I'm labeling human points here with these red circles. We can see here that at a very low contrast setting on the x-axis, the human performance is terrible. The accuracy is very low. But in the cases of the VGG network, they're barely impacted at all. The performance is almost perfect. So this is really good news. What's really curious, though, why I say this is a curious contrast deficit, it's the opposite case for increasing contrast, right? This is something that doesn't affect human vision that much. There is an effect, but it's not drastic like decreasing contrast. Here, the networks are more impacted by that, which is really strange. But they're still better than the low contrast setting overall when we get to extremes. So this is not as bad as the transformation. So again, a very, very operationally relevant finding, something that would be very, very difficult to discern from standard data set testing. And you can do this again over a whole bunch of different conditions. Here I'm showing you just some summaries of a normalized area under the item response curve for a number of different conditions. And looking at, image processing operators like we saw, so sharpness, contrast, brightness, additive sources of distortion, right, like linear occlusion, and also salt and pepper noise, right, or any noise could be used in this same regime. It's kind of well known that that affects deep learning-based systems quite heavily, and we've observed that. So you're doing worse here, right, if your normalized area under the item response curve is very, very small. Different scale, rotation manipulations, and then again, contrast, et cetera, can be manipulated in either a bounded or unbounded manner. So we've looked at both of those things. But the point here is that it's easy to create really nice summary statistics that are almost as convenient as the traditional summary statistics. Just have to get people to understand what these represent versus what those other metrics represent. Okay, so you're not just restricted to things like object classification when you're dealing with psychophysics on the model. You can also do this in a face recognition context. So this is also work that was led by my graduate student, Brandon. This one in collaboration with Ali Kwan from Perceptive Automata, one of my former students from my lab, and Sam Anthony again. And this was a paper that appeared at ECCV 2018. So for face recognition, you have to take a few different paths to build up the experiment, but it's very similar to what you do in object recognition. The major consideration here is the preferred view issue. Typically with faces, this isn't quite the thinking that we use, right, to do facial analysis, because the face images are almost always full frontal face images. That's how we assess identity. So that means we have to deal with some other considerations when it comes to biometrics, right? This is a long-standing area of study in computer vision, and we know that there's some different considerations that need to be taken. So what do we do in an evaluation context when we think about different classes of users that may impact the system? So number one, right, we're dealing with, in many cases for standard evaluation, something like a receiver operator characteristic curve. and we have thresholds, and we try to balance the true positive rate with the false positive rate at some operationally relevant setting. What's interesting about this is it leads in many different scenarios to different classes of users within the system. So what does that mean? In the biometrics literature, you'll find descriptions of what is known as Doddington's zoo, which classifies different user bases based on their error rates that are tied to this form of analysis. And typically we find 4 different categories. We have people who are goats. This means the system has a lot of trouble recognizing who they are. For some reason, they are falsely rejected quite often, and that becomes a big problem for usability. We also have 2 other problematic cases with respect to security, right? As we think about face recognition oftentimes in an authentication context. We have these users who are known as lambs. They are easily impersonated by other users, right? There's something going on with the false accept phenomenon. And then we have wolves who easily impersonate other users. So all of these are problematic with respect to the false accept rate and the false reject rate of the system. And then we have sheep. These are the good users. They are not strongly impersonated by other users. They are not strongly rejected by the system under normal operation. And so what we need instead of a preferred view is an optimization routine that will mine our data set, right, where we're trying to get our stimuli from, to find all the sheep, right, all the good behaved users, because we know those are going to be at a good place in terms of the operation of the system, and those are the users we want to reduce their performance by adding the transformations to the images, right, perturbing these images in some way for the psychophysics piece. And that's exactly what we do. And then ideally, right, we'll have some sense of how well these systems perform under a whole range of different conditions, which we may experience in the real world, right, which is very important if we're doing, say, mobile authentication on a cell phone. So we conducted a bunch of experiments in this context, looking at different face recognition models. Here we have VGG face. We have, which is very standard deep learning based model, OpenFace, an open source implementation of Google's FaceNet. FaceNet, which is a second open source implementation of Google's FaceNet. SLM Simple, which is a shallow network with randomly instantiated weights. It was randomly screened as opposed to being trained directly from data on the labeled faces in the wild data set. So it's an interesting way to screen a neural network. And then OpenBR, which is using handcrafted features, at least the version that we use. So something that is not deep learning based. And as you see here, right, we see the item response curves just like we did for object recognition. They look similar. We have more human points here on this plot, FYI. But we can see here several different things. Number one, there's a lot of, for these particular conditions of Gaussian blur and brown noise. Brown noise, if you're not familiar, this simulates Brownian motion in the noise pattern. And it puts more energy at lower frequencies. There's a tremendous amount of variation between the different face recognition systems here. And number one, these things were trained on different data, right? So that could explain part of it. But what's really interesting, I think, we have 2 implementations of the same algorithm, right? 2 implementations of Google's FaceNet, two open source implementations. Those would be the green and magenta curves. There's a huge gap between them. So think about that, and I'm going to come back to an explanation as to why that's happening. It's very puzzling. I'll mention that both of these algorithms produced roughly the same scores that were comparable to what Google posted for labeled faces in the wild, a standard face recognition benchmark in the publication. Looking at the summary statistics, this would have matched, right? But they're clearly very different. Also really interesting, as I mentioned, we have a system that is not deep learning based. It seems to be quite better than some of these deep learning systems, right? OpenBR, in both these cases, is one of the best algorithms. SLM Simple, a really strange neural network, right? That's not trained with backpropagation in the traditional way. It seems to be very tolerant to noise and does pretty okay when it comes to tolerating Gaussian blur as well, though it is impacted somewhat. But it's not as bad as, say, that magenta FaceNet implementation of Google's FaceNet. And human data, in some cases, humans are superior, but Face recognition is definitely a case where I'd say machine performance in certain settings is better than human performance, right? And these psychophysics experiments bear that out. That's a claim that's been made over and over again, especially in the popular media. But in these cases, it's actually true. So something to keep in mind. As I mentioned, right, if you're doing these manipulations, right, these perturbations, transformations of the images, you're not constrained to just the simple image processing functions, right? We know you can do more clever things. What if I could incrementally blink an eye, blink left or blink right? What does that do to the system? Ooh, does some really bad things to some of these recognition systems. Looks like BGG Face and SLM Simple, very, very tolerant to this, right? They basically are not impacted at all, which is very, very interesting. But everything else is strongly impacted in some cases, which is surprising, right? Because this isn't a very drastic change to the image, right? It's just a blink, something very natural, something we would expect in the wild, right? In some cases, it doesn't even take a lot of blinking, right? It's just a very slow closing of the eye. Like, those early moments of the blink are already impacting some of these systems. I would say part of the explanation there is training data, right? You don't typically see blinking in face recognition data sets, right? Mainly because these things are crawled from the web. People upload their best selfies, right? Why would you put a photo that's sort of ruined by a weird blink, right? It's sort of an outlier case. It's one potential explanation here. Humans, as it turns out, had a lot of trouble with these images too. I would say that the human forms here, though, is more of an artifact of using these 3D rendered heads, something to keep in mind. And again, a whole range of different things. Again, if you have a good 3D graphics package, right, some sort of good rendering engine, you can do things like different expressions, different emotions. Here we have fear and smiling. We can look at some of the things we looked at before, like contrast. We saw the same effect. The face recognition models, with the exception of FaceNet, were strongly invariant to this, but humans, right, definitely were strongly impacted. And then looking at other forms of noise as well. Pink noise is similar to the brown noise scenario, but it's just not as intense in terms of putting energy into the lower frequencies. But again, these are all common things that are studied in the signal processing world, and things that have been demonstrated to really cause problems in these convolutional neural network-based recognition systems. Okay, so coming back to the mystery of OpenFace versus FaceNet, as I mentioned, right, this is sort of puzzling. Things were supposed to be the same, right? Never trust GitHub, right? You got to dig into the code. Don't just look at the READMEs. We looked at the implementations in exhaustive detail, and this is what we found. OpenFace made use of Cassia web faces and Face Scrub for training data. FaceNet used a subset of MS Celeb 1 million. Those are different data sets. OpenFace is an exact architecture match to Google FaceNet, what's in the paper. The coder who created FaceNet took some liberties in the implementation and included some Inception ResNet v1 layers. That's not in the original paper. OpenFace uses dlib landmark detection and alignment. FaceNet doesn't do any landmark detection or alignment. So major, major differences, even though on the surface, both appear to be correct because they matched the summary statistics that were reported by Google in the original paper. Something we would have never figured out without doing these psychophysics experiments. All right, so just to wrap up here, I want to mention one other case where we've looked at psychophysical measurements in the context of visual recognition. And again, something that's very useful, I think, for autonomous system development, because there's a lot of interest in doing recognition from UAVs, and this work touches on that. So this is bridging the gap between computational photography and recognition. This was work that was led by two of my graduate students, Rose Vidal-Mata and Shreya Banerjee, with some assistance from Brandon, our resident psychophysics guru. And this is going to appear in TPAMI later this year. All right, so what are we talking about here? An idea that's been floated out there in computer vision for recognition is, why don't we use some techniques from computational photography like deconvolution, super resolution, to enhance images, to clean them up if they're a little bit noisy, if they're low resolution, to ideally get a better recognition result, right? So you take the original corrupted image, you enhance it in some way, and then ideally that corrects a misidentification of whatever's in the scene. That is all well and good on the surface, but if you try to do this in practice, oftentimes you end up with more artifacts than what you started with, and that creates a big problem. So what we wanted to understand is what kind of changes to images do people prefer, and what kind of changes to images do artificial vision systems prefer? Is there any consensus there, and can we use this information to ideally make some progress on this problem? What's interesting, we're starting to see in the literature a number of techniques that have joint optimizations for both of these things. So something that is going to try to simultaneously train a restoration and enhancement component and a visual recognition component all in one. And this only works if you have some good notion in terms of how well you're doing to improve the image. But the motivation may be, I'm less concerned about the way this looks and more concerned about the final recognition decision. So if the output of the network in terms of the enhancement piece looks a little bit strange, but it gets a good recognition result, maybe that's okay. But we still want to understand how that's different from human perception, right? Because there may be some problems lurking there. And so this middle panel shows that overall idea. And then once you have the system trained in operation, it's just a matter of taking the original corrupted image, enhancing it, recognizing what's in the scene, getting that output, and that's your final decision. So we designed a psychophysics experiment for people to look at this by doing just a two alternative side-by-side type of task. But instead of having you choose one of those alternatives, if you're a subject, you get to rate these comparisons on a Likert scale. So, is the image X much better, the same, worse, or much worse than Y? That's the question that's posed, just a Likert scale. And then we can take those measurements from people and bin them, right, into 1, 2, 3, 4, 5. And then we can put this into a scaled representation. And we ran a whole bunch of studies related to this, where the final rating for the enhanced image is the mean score from approximately 20 observers. Now, if you dig into the literature, especially the literature that crosses over between computational photography and visual recognition, there have been some alternatives proposed. One of them is the Learn Perceptual Image Patch Similarity metric. So this is an automatic metric which is meant to simulate what human assessment would be in a perceptual sense on the same type of two-image task. So with a network, right, that's able to assess the distance between two image patches, you can measure the perceptual similarity between them, getting a score ranging from 0, meaning they're exactly similar, to 1, meaning they're maximally far apart. All right, so it's just a scaled or normalized distance. This is a really cool paper because it does conduct a bunch of psychophysics experiments to try to validate this. Now, this network is not perfect, and the authors of this paper, which came out at CVPR 18, do not make that claim. But it's pretty interesting that it captures some of that variance. And so what we wanted to understand is, given our psychophysical regime, it's a little bit different than what was proposed by Zhang et al. They looked at a two alternative force choice task and an assessment of some of the image features, and not necessarily a Likert-based setting. What happens in that setting in terms of correspondence, right? Because these are all different ways to measure human vision. So what we did was collect a data set. In this case, we collected a data set from aerial vehicles and also a ground collection. So we have video from UAVs, we have video from fixed wing gliders, and then also a controlled ground collection. We ran this as a challenge, a prize challenge at CVPR 2018 and 2019. And the idea was, again, to do restoration and enhancement to improve visual recognition. But we started again with these psychophysics experiments because we understand human perception. Do humans perceive any difference? And do they perceive that difference to be better or worse? And what we found was quite fascinating. So because this was a prize challenge, we started off with a number of baselines, which we computed, right? Different types of algorithms, some deep learning based, like very deep super resolution, like super resolution CNN, some classic techniques like nearest neighbor, bicubic interpolation, bilinear interpolation, and blind deconvolution, right? The standard off-the-shelf tools you would use. And then we compared those against a host of different novel algorithms that were submitted to the competition. Some deep learning based, some very, very simple. And what we found across the board was that in most cases, these techniques to humans are making the images worse, right? Which is not the message, right, that computational photography has been telling us about. Even the standard methods, right, in the literature, they should typically make things better, but that's not the case in terms of human perception. We wanted to look at how our results stacked up against the automatic machine-derived results. So looking at this LPIPS metric proposed by Zhang et al. And what we found is that there was quite a great deal of consistency. We saw a good correlation between the human ratings and the machine ratings, but that wasn't always the case, right? Here's, if you look at the plot here on the left for baseline algorithms, looking at the circles labeled BD for blind deconvolution, there was some disagreement between the human ratings and the LPIPS ratings for many of the cases. But if you have a better behaving algorithm, so blind deconvolution was one of the worst algorithms that we assessed here. If you get a lot of consensus, we see that these two methodologies, right, the psychophysics, Likert ratings, and the machine-derived similarity are more in line in terms of what they're telling us. We did this across different partitions of our data set. We did this across many different algorithms. And what we saw was really interesting. The tight clustering for the ground collection is indicative of how easy that data set is compared to the other two. The glider collection was much higher resolution, much cleaner in terms of noise compared to the UAV collection, which was crawled from YouTube. This kind of bears that out, right? So hand in hand, using an automatic metric and a human rating, you can make a lot of progress on the evaluation side of this, this problem. All right, I'm just about out of time, so let me just leave you with a few thoughts for autonomous systems. There is a large disparity between dataset performance and real-world performance. Think self-driving cars in 2020. Why can't I go out and just buy one, right? I mean, Tesla will sell me a system, right, that's purportedly autonomous, but it's pretty dangerous, right? You know, you have to have your hands there on the wheel at all times. You have to be vigilant. I can't just fall asleep and let the car drive me to my destination, right? Why is that the case? All of the systems that are being developed in the industry are data-driven. They're based on these data sets, and we have this disconnect. That's a big issue. Visual psychophysics is a primary tool used to study vision in psychology and neuroscience. Why aren't we using it in computer vision? It would seem to make a lot of sense, right, to get in line with the rest of the vision fields and add this to our toolkit. And what I'm suggesting isn't to just ditch the data sets. They have no value. That's not true at all, right? Data sets are still important. They give us information to use for training and evaluations. Why not combine the data sets with psychophysics-based evaluation? It seems like a good idea. Try it out. All right. If you have questions, come to the workshop's live session on August 28th from 0 to 2 UTC +1. And I will be there live and in person, happy to discuss these ideas or any other ideas or questions that you may have. It will be a panel session, so it'd be good to get some discussion going. I'm sorry I can't be with you in person, but the pandemic happened and we're doing these virtual conferences now, but we'll see how this goes. CVPR seemed to work out with the virtual Q&A, so I think this will be smooth for ECCV. And if you're not able to make that live session, but you still want to contact me and ask a question or give me a comment, please feel free to send me an email. I'm very, very accessible via email. Just shoot me a message and I'll be happy to respond. All right, so thank you and hope to see you at the live session.